I will talk about why in OCD system we need to care about the dispersion. That means if there is a dispersion in OCD system, why we need to take care of that and why that's happening. What is the cause of dispersion? Today I'll talk about that. Light is a photon, and say in our OCD setup we use the visible light around wavelength around like 800. But in general, if you look at the visible wavelength light, it has different wavelength and different color of light. So it starts from violet. The wavelength is around 380 to 450 nanometer, and it goes all the way to the red light, and its wavelength is 620 to 750 nanometer. So one thing that you can see that as the wavelength increases, frequency decreases. If the lambda increases, then the frequency of the light decreases, and if the frequency decreases, and we can see that like in this way we have like increase of energy. We don't need to think about the energy, but it's good to know. Anyway, so where the dispersion is coming from, let's talk about something. Say in normal vacuum, the light will always travel with fixed speed. That's 3 e to the power 10 meter per second. That's fine. But when light will travel through a medium and whose refractive index is not same as air, usually the refractive index of air is 1 and other medium is different. If light pass through any medium whose refractive index is n, then the speed of the light will be the light in the vacuum, that's C. Sometimes we call it C naught 2 divided by refractive index of that material. Now say for example that light is traveling here in the air, whatever the speed it has. If it is travel through the order, as we know that the refractive index of order is n equal to 1.33, that is, it's greater than 1. That means C by n, whatever the speed of light divided by n means 1.33. It should be less than whatever the speed of the light at vacuum. So it reduces. So 186K, from 186K it reduces up to 140K. It reduces to 140K. What about glass? We know that refractive index of glass is 1.4, so it's even higher than order. So it reduces further. Diamond has like increase of refractive index, like more refractive index, so it reduces further. So as the light passes through different medium, the speed of the light changes. And another thing to notice is that the speed of light is different for different wavelength, because when light passes through any medium, the refractive index that it introduces, that it faces, or the refractive index for a material is different for different wavelength. Say if light passes through the order, then refractive index of red light might be say x1, and the refractive index of violet light may be x2, and x1 and x2 will never be equal. So usually the refractive index of the red light is less than refractive index of violet light. So if it is less than, then if you look at this equation, So Cn, right? If this is less, if this n is less for the red light, that means speed of red light will be always higher than the speed of violet light. So speed difference. So speed is high where the n is low and vice versa. So what to do with that? So why we are talking about that? What is the speed of light causing when its light is transmitting from one place to another place? So here is just further analogy. Say like one car is moving at like 65 mile per hour, another is 55 mile per hour. If they start, and after certain amount of time, this car will be reach earlier than the red car. Just an analogy that how light will pass. So one kind of light will pass faster, another will be pass slower. Same thing happens. Say we are sending some optical signal. So this is the signal we are sending through the fiber, which is dispersive material, and this wavelength will be changed. As we know that wavelength travels at different speeds. So is here as the time passes, the speed, as I mentioned here the speed between two cars, as the time progresses, the difference between two speed as difference from here to here, the difference in terms of mileage is different, in terms of distance is different between two cars. Same thing happened for the light. As the light passes over different distance, and we can see that as it passes, it becomes broadened because the speed of the blue and red portion of the light is different. So that's one problem, that we are not getting all the light in the same position. So that will cause the chromatic dispersion. Let's look at the OCD setup, how the OCD system send the light. So this is our laser source. This is the laser source. We are sending light, and here is a fiber beam splitter. One, say if this is 50-50, just for example, if it is 50-50 beam splitter, that means that 50% will light pass through the reference arm, another 50% of light will pass through the sample arm. It will come to the sample arm and it will reflect it back and from the sample, and it will go through this camera, and also from the reference arm. This is reference arm, light will be passed through this path and they will combine here. After passing here, and line scan camera will detect the light. Now here is the thing, as we know that when we detect the interference pattern from the line scan camera, both the reference arm as well as sample arm are passing through different path length. That means in reference arm and the sample arm path, the amount of glass or the fiber is different, which means that they are experiencing different amount of dispersion, because as the glass amount is different, that means medium is different. If the medium is different, then although we are sending the broadband light source, say for example like this kind of light source, but as the medium is different in the reference arm as well as the sample arm, so when they will combine here at the returning path, when they will combine, then they will not combine in same way because of the dispersion of the different materials. So if we can make sure that both of the path is experience the same amount of glass, then the dispersion that will come, that will be very negligible. So dispersion we can tolerate if both of the path it has the same amount of glass or same amount of medium, so it can be good. But problem is that, say when we build the setup, we can build the setup and we can make sure that the reference arm and the sample arm have the same glass by introducing, say, more amount of glass in the reference arm or either the sample arm. But when we will image in different samples, say one day you are imaging with brain slice, another day you are imaging with agar or the Drosophila sample. That means when we will change the sample, that means that we are changing the refractive index in the sample arm. So due to the changes of the refractive index, when the light is combining in the camera, in the returning path, that means same thing is happening. That means they are not, there is a delay from one arm compared to another arm. There will be a group delay of the light. That means there is a chance of dispersion. So there will be a dispersion mismatch. And so that's a problem, that dispersion will be happen even though we initially match the glass. If we use only one single sample all the time, and if we know that that sample has certain amount of refractive index, then probably we will not have that issue if we introduce extra glass in the reference arm path. Otherwise there will be issue. In next video I will talk about the solution. I will talk about I will first talk about the hardware solution, then I will talk about what are the software solution we can have without introducing any kind of extra glass. Thank you very much.